of MRI, and I'll just go through the basic concepts which would be sufficient for us to understand how an MRI image is formed. So the first concept which we need to understand is that of spin. So like all the atoms in nature have some fundamental properties like mass and charge. Similarly, spin is also one of those fundamental properties. It is also known as angular momentum, and all the individual unpaired electrons, protons and neutrons, all of them possess a spin. It is denoted either as plus half or minus half depending on the orientation. So the important point here is that two or more even number of particles, if they have opposite sign of spin, they'll eliminate all the manifestations which an individual proton can or neutron can produce. So what I mean is, if we have a system in which we have 4 protons and 2 of them have plus half and 2 of them have minus half, then the manifestations of the spin will not be observed because the net field will be 0. So what should be the criteria for using the nuclei in MRI? Like, how should we select a nuclei? So in NMR, it's only the unpaired nuclear spins that are of importance. For example, the nuclei which have odd number of protons or neutrons, the reason I just gave. More specifically, if the total number of protons is odd, then only the nucleus will have an angular momentum and hence the spin. And that is how we will eventually get an MRI image. So if we think about the common nuclei which have odd number of protons or neutrons, we can think of hydrogen 1, carbon 13, fluorine 19, etc. So in practice, only hydrogen 1 is used for imaging. So what's the reason? The most basic reason that we can think of is that hydrogen atom is a component of water and fat, and water constitutes about 2/3 of the body, and therefore it has a lot of potential signal which we would not be obtaining from other nuclei. And the hydrogen atom satisfies all the requirements that we need. Its proton has a spin, it rotates around its own axis, which makes it act like a tiny magnet. As you can see here, it spins on its own axis and it acts like a magnet. It has a magnetic field of its own. Okay, so now it's important for us to know how protons behave in various conditions. The first one is in the absence of external magnetic field. Suppose there are a number of protons in free space. In such a condition, the protons are randomly oriented. They do not have any specific orientations. This one is in the longitudinal direction, this one, it's all randomly oriented. And as there is no magnetic field acting on the system, there is no net effect on the protons. Secondly, now we see how they act in the presence of an external magnetic field. Now this we can relate to the MRI system, because in MRI system we do have a magnet which has its own magnetic field. And we call the magnetic field as B0. So in presence of the magnetic field, the protons tend to align themselves in the direction of the external magnetic field. So this alignment can be either parallel or anti-parallel. For example, this 1, 2 and 3. These 3 protons are oriented towards the parallel direction of the magnetic field, and the other 2 are anti-parallel. The parallel oriented protons are of low energy and the anti-parallel are of high energy. So inside the MRI scanner, as we saw the image of the MRI machine, the magnetic field runs down the center of the tube in a horizontal direction. So you can imagine that when a subject is placed inside the machine and when the main magnetic field is turned on, the hydrogen protons would line up either in the direction towards the head or the feet. Now, as I said before, if we have a condition in which we have even number of protons or neutrons, the manifestations will not be observed. But it is always observed that in nature, there is always a slight excess of protons which are oriented in the direction of the magnetic field, that is parallel direction. And the net resultant magnetic field, because of such protons, produces a magnetic field which is denoted as M. And this M is what we would use to generate an MRI signal and eventually an image. So what I just said we can understand through a small video. So this is the direction of the magnetic field in the horizontal direction. So as you can see, the protons were initially randomly oriented, but under the influence of the BO, they tend to get parallel to the magnetic field. Now, one thing which is not shown in this video is that they have shown all the protons in the parallel direction, but in fact there are many of them which are anti-parallel, but more of them are in parallel. We need to understand the basic coordinate system that is followed, because the next few slides will be using the coordinates. So if we imagine this to be the direction of the main magnetic field, the direction parallel to B0 is called a longitudinal or Z direction, this one. Similarly, the plane which is perpendicular to this direction is called a transverse plane or an XY plane, which is perpendicular to the longitudinal direction. This is a very important topic in the physics part, a phenomenon known as precession. So this motion that you see, it basically depicts what is known as precession. So to understand it more clearly, you can imagine a spinning top. I'm sure we all have seen a spinning top. So we have observed that at a specific point, the top begins to wobble around its own axis just before it's about to fall. So the thing that's happening there is that the combined effects of gravity and the spinning motion cause the top to precess. The same phenomenon occurs in the nucleus. The protons are revolving around its own axis. Under the influence of a magnetic field, they eventually tend to precess. And this precession occurs at a specific frequency known as precession frequency. So why do we care about the frequency of precession? So up to this stage, we have got all the protons in the direction of the main magnetic field. Now, in order to get a signal from them, we have to do something. We have to perturb the system. We have to disturb the system such that we get a response back, that we can record and form an image. So this frequency of precession is also known as resonance frequency. It allows to create a situation through which the resonance phenomenon can occur, and through which we can efficiently transfer the energy to the protons and record the response afterwards. And only at this frequency does the nucleus absorb or emit energy. So it's really important for the resonance phenomenon to occur. And so how do we determine what's the resonance frequency? That's obtained by an equation known as the Lamore equation. So this is the Lamore equation. It says that the frequency of precession, that's omega 0, is directly proportional to the external magnetic field, VO. And the constant gamma is known as the gyromagnetic ratio, and it is a characteristic of each type of nuclei. All the nuclei have their own specific values of gamma. So we can calculate the frequency of precession for all the nuclei individually. So in MRI we use hydrogen 1. So how do we calculate the resonance frequency for hydrogen 1? So we know that most of the commercial MRI machines run at a magnetic field of 1.5 Tesla. So we can just put this value as B0, and the value of gamma as 42.57 megahertz per Tesla, and eventually you can get the value of frequency of precession, which comes around 65 megahertz. So what it means is when we subject an electromagnetic radiation at a frequency of 65 megahertz, the protons which are in the field will undergo resonance. So this shows as we said, this is a Z longitudinal direction, the same direction of the external magnetic field. This is the pattern in which the precession occurs, and the omega 0 denotes the frequency at which this phenomenon occurs. as we said, it's the omega 0 is directly proportional to the magnetic field. So for any given value of the external magnetic field, we can determine what's the resonance frequency